Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure today to introduce Ramesh Gopinath from IBM Research in Watson. He heads one of the speech recognition groups working on a bunch of different techniques on adaptation as well as Gaussian modeling, and they do a lot of work on embedded systems for automobiles and telephony servers interacting with the product groups. And we've been wanting to get Ramesh here to come and give a talk for some time, so he graciously volunteered to take advantage of this trip to the West Coast and spend a day with us. So we have a full schedule for the rest of the day, so I'd appreciate everyone in the schedule to keep time. Don't delay, otherwise he'll miss his flight. So without further ado, Ramesh.
Thank you very much, Alex, for inviting me, and it's a pleasure to be here. This is the first time I've been to Microsoft Research, and the good thing is a lot of the faces I see here are familiar, either because I've known people for many years, or I've known them for just one day, because I was at the University of Washington yesterday, and I did meet a few, at least one person who's sitting there. Okay, so in this talk, basically, this is some work that I've been sort of doing with a bunch of people over the past, 5 years or so. It's a theme that we've been trying to push for several years, trying to see how far we can take it. And the collaborators are Scott Axelrod, who is actually at a hedge fund, and the rest of the people are at IBM Research in my team. The talk is going to be in two parts. The first part, which will be the bulk of it, I'm going to go through a set of techniques that we have sort of, a set of increasingly complex models that we have built for Gaussian mixture modeling in general. And these ideas can be applicable, I think, in any place where you use Gaussian mixture models. And specifically, we are using it in the speech recognition context. And remember, there are many other ways in which you can model distributions and for speech recognition. But this is the most popular, and that's what we focused on. Additionally, the only criterion that we are going to focus on this talk is maximum likelihood. Certainly, the same thing can be the same trip you can go through with discriminant techniques, and we've done that too, and you get good results. The second part of the talk, I'll focus on something that I'm very excited by. It's more recent work on how to adapt the models once there are mismatches between training and testing. And it's a very important area from a practical perspective, and some of the things we've done I'll touch upon. So since most people here are in the speech area, I don't need to spend much time. But nevertheless, this is what, to just set the stage. You have four components in a typical recognizer. A signal processing component that takes the audio waveform and creates some features. Then you have a search stage that uses these features to produce the words using two knowledge sources, the language and acoustic models respectively. The first part of my talk is going to be focused purely on the acoustic model, like Gaussian mixture modeling. And the second part is on adaptation of the front-end signal processing. Okay, so acoustic modeling, right? So the basic idea here is you have to model each of the states in a hidden Markov model, and a state typically being your context-dependent phonetic state. And what we do, and what state-of-the-art systems do, is you model it as a Gaussian mixture. And if you rewrite it slightly differently from using the standard mean and covariance parameters in terms of the precision or inverse covariance and this new thing which I call the transformed mean, which basically is the precision times mu, or in other words, sigma inverse mu. What you notice is that in terms of the data-dependent terms in the Gaussian exponent depend linearly on these parameters. And so, in other words, these are the natural parameters of the Gaussian and the exponential family. It's a very critical thing that we exploit in the rest of this talk. And I think after going through this over the last 3-4 years, I'm convinced that thinking of things in terms of means and variance is just simply the wrong way to go about things. Okay, so what are some of the issues in Gaussian mixture modeling? Fundamentally, it boils down to basically these are the parameters of Gaussian. You're modeling them with means, covariances, and priors. You want to estimate the parameters, assumptions, maximum likelihood. But some of the issues you run into are the fact that from computational reasons, storage reasons, and robust estimation considerations, you typically tend to use only diagonal covariances in most state-of-the-art systems. Well, pretty much all state-of-the-art systems that are used, at least deployed. So that's the reason for that is very simple, basically because if you use a full covariance model with about 100,000 Gaussians, which is typical in most systems, you're running into like half a gigabyte to just store the model. It's not going to happen in most practical systems. And so people tend to use diagonal covariance models, and there is a variety of tricks that people use after you build a model. I'm not going to go into any of those techniques. Just a priori building a model, you want to do it efficiently, and what can we do about it is what this talk is going to be about. So people tend to use diagonal models, and the question is, can we do better? So this was way back in about 1998 time frame, an idea that basically I explored, which was, can I find a linear transformation of the data that makes it approximately diagonal? Again, people have come up with the same sort of idea from different areas, and I'm not going to that. I'm just going to go with the way I had viewed this problem, which is, you can view this as constraining the covariance to be in this fashion, meaning finding some transformation that diagonalizes things, equivalently in terms of the inverse covariance or the precision matrix, where lambda is this inverse of the diagonal covariance. So lambda is basically made of inverse covariances along the diagonal. What you notice is that the precision is being written in this form, which can be equivalently written in this slightly different form as the sum of outer products. Very simple idea, but the point is this gives you a very clean interpretation of what you're doing. What you're doing is you're trying to expand the precision of a given Gaussian in a basis made of these rank 1 matrices, symmetric matrices, and these are the coefficients of the Gaussian in that basis, right? So that is the basic idea of this maximum likely linear transformation. It works. It's one of those few techniques that I've noticed with Gaussian mixture models that works across the board in every data set that I've tried. This is one of the very few techniques that works universally. Tried it in speaker ID, in every data set for speech recognition, in image processing. In every place I've tried, this is a big win. And so somebody who doesn't do MLLT is clearly doing something wrong. You can do much better. Anyway. The reason why, so remember the way I approach this is from the point of view of a transformation that diagonalizes things. But after rewriting it as a basis expansion of the precision, suddenly, a whole lot of things, possibilities open up, which is I can, instead of using a square matrix here, use a rectangular matrix, basically, which is very thin and horizontal. Think of it that way, right? So there are many more columns. That basic idea is that in this basis expansion, what if I use more rank 1 symmetric matrices to expand? In other words, instead of using little d, which is the feature space dimensions, use capital D sub p, which is a dimension of the precision. That's why it's d sub p, where d sub p ranges somewhere between little d, which is what we typically do for MLLT, and all the way down to the total dimension of a covariance, which is d into d plus 1 over 2. If you do that, basically, so that's the basic idea of the EMLLT model, extended maximum likelihood linear transformation. There's no transformation here, really, right? It's just a basis expansion where you've increased the size of the basis. The good thing about it is basically with this model, it includes the standard diagonal model by just taking the A's to be the standard unit vectors. The MLLT is a special case of this. And more importantly, as it becomes the full dimension, it can model any full covariance. So it's a very flexible way of going all the way from diagonal, which is what people have always used, to the full covariance in a nice flexible fashion. And the other things that are interesting about it, and in this entire talk, I'm not going to talk about any estimation technique. It's all published work. You can go look at the literature. There's a bunch of nice tricks to both estimate the basis as well as the coefficients. In fact, there's some very interesting math also that comes out. Like, for example, to expand the basis, we were actually quite excited by the things we had to go into. It comes up with a quadratic eigenvalue problem we have to solve, blah, blah, blah. But the details essentially are not important. So this is a basic model. And it gave very good results on a few data sets that we tried, and I'll share some of the results. Okay. There is another very interesting interpretation. Remember, so the lambdas in this EMLT model is no longer has this inverse covariance interpretation, right? And the reason for that is some of the lambdas could even be negative, okay, if you at the maximum likelihood solution. But nevertheless, there is a very nice interpretation of what's going on, which is another way of coming up with the same thing, and that's what I want to stress now. So to understand that, if you think of a standard maximum likelihood estimation of a diagonal covariance, what you do is you can either say it's an ML estimation process, or you could say, look, I have a set of constraints I satisfy, and these constraints are the sample variance along the unit directions match the model variance along those directions, right? That's what this says. So that's one way of interpreting ML for diagonal covariance. For EMLT, it's exactly the same thing. What you do is you have a set of directions, the A sub case. Each direction, if I make sure that the variance along the A sub k direction from the model predicted by the model and predicted by the data are matched, right? That gives you that's all the degrees of freedoms you have. That uniquely specifies the lambda, and that basically is your EMLT model. So you don't have to think of maximal likelihood at all. It's basically, you can view it as these constraints are satisfied. So it's very intuitive. So you pick a bunch of directions and make sure that whatever model you choose has to satisfy that the variance along those directions match the sample variance. Then you get the EMLT model by default. So there are two parts to it. How do you choose those directions, and how do you choose the coefficients of each Gaussian? And both of them basically, like I said in the previous chart, you have standard ways to do this.
So in practice, you decide the dimensionality based upon the amount of data available?
We don't have a recipe for this. Essentially, you scan a bunch of sizes and you pick up the one that gives you the best model. In fact, as the dimension increases, you can actually have overtraining, and you can actually see these nice curves. So you can automatically pick these in a data-driven fashion. But if the model supports full covariance, you won't see overtraining, right? If the data supports, the full covariance, because the extreme cases you approach full covariance.
And also, you mentioned earlier about discriminatory distribution, like you talked about.
Yes.
Just curious. Does this concept generalize to discrimination?
Absolutely. The model is exactly the same. The only change is how are you going to estimate the basis and the expansion coefficients, right? And both the basis and the expansion coefficients can be done in a discriminative fashion. In fact, for the entire family that I talk about today, except for the last part about nonlinear transformations, you can use exactly the same framework, and we have proved that basically it's possible to do. The proof is very hairy, but it's irrelevant. What is important is you can use the same constant d for those who are familiar with things. Okay.
So this sounds like you define a family of probability distributions that satisfy these linear constraints, right? Sort of like what's done in maximum entropy, or not really?
In fact, good point. It's exactly that. In other words, there is a duality between maximal likelihood and having certain linear conditions satisfied.
Yeah, so
these are the linear conditions, exactly. It's the dual, exactly.
And the dual problem is the maximum likelihood?
Correct.
Problem.
That is correct, exactly.
Okay.
Yeah, but it's, what I wanted to stress is that these linear constraints are this intuitive thing of variance along directions being matched, which is what I wanted to stress. That's the only point I was trying to make. Otherwise, yeah, exactly right. Okay, so if we could do this, come this far, meaning have it as a basis expansion, we could do one more simple thing, which is, okay, so I have the precision expanded like this. The only change is why am I using these rank 1 basis elements? True, the rank 1 has this nice interpretation I told you, but who cares about interpretation in this business? We care about performance, right? So this was the next innovation. Said, why don't we just let it be a general symmetric matrix? Go on.
The P to be positive definite?
But if you want to have a Gaussian, P has to be positive definite, right? In the previous case, since, remember I said some of the lambdas could be negative, but if you do the optimization correctly, the maximum likelihood value will be such that the precisions will be positive. Okay, so but in the optimization, if you use a numerical technique, you got to be careful to not. That's why I said you solve a quadratic eigenvalue problem to realize the bounds in your line search. How far can you take before you hit the boundary when the determinant of PG is 0? So that's the part. Okay, yeah. So here basically these are arbitrary symmetric matrices. There's no constraints that their eigenvalues have to be positive or anything like that, right? And putting any constraint like that, we can even show that it's not the right thing to do, because all you care about is that the precisions themselves are positive definite. Everything else is irrelevant. So this, just the same trip, obviously it generalizes diagonal covariance. It's clear. EMLT also generalizes, it's clear. And this is another way to model full covariance in a smooth fashion. One additional point I want to make is, if you look at the precisions, right, they depend linearly on the coefficients for fixed S and vice versa. So it turns out that, and since the parameters depend sort of linearly, it turns out that since the exponential model, the likelihood function is convex, in this particular case, you're going to see that the likelihood of the data is going to be convex in both the parameters fixing the basis and vice versa. So you have a nice convex problem. You have unique answers through the entire process. So there are no issues. I'm just saying it's a very simple numerical problem to deal with. However, in the EMLT case, it depended in a slightly different fashion on the A case because it is quadratic. And therefore, you don't have a convex problem, but nevertheless, you can solve it using numerical methods. So this is a little nicer as a model. But that is nicer from the point of view of computing because, like I said, it's like computing variance along certain directions, and it's basically like a standard problem. Yeah?
Ramesh, can I ask a quick one? When you have the second case where you have those generic AKs, would you want the set of AKs to be orthogonal?
No.
Not necessarily?
No. The A case in general, to get good performance, it will not be orthogonal if you do it in a maximum likelihood fashion. Yeah, the A case are not orthogonal. So the idea is related to the following. If you have two matrices that you want to simultaneously diagonalize, then you can do that. One matrix, obvious, orthogonal you get. Two matrices also you can diagonalize, but you know for a fact that you don't get orthogonal directions that simultaneously diagonalize two of them. In this particular case, what you have is you're approximately diagonalizing a whole bunch of guys. So it's really an approximate diagonalization which has an actual interpretation as a maximum likelihood technique. Okay, so that's basically this. So what we call this the precision constrained GMM. The basic idea being the precisions are constrained to be a subspace. In EMLT, it had more constraints. They had to be rank 1 bases and stuff like that. And this is the most general model that I wanted to talk about today from the point of view of extending this scheme, and which is you just view this as, say Gaussian viewed in the exponential family as, e to the sum theta transpose f. Theta depends obviously on the Gaussian, and f is some function of the features, which is basically this quadratic function of the features. And this is your standard Gaussian, and this is basically the normalizer, essentially, the k. Okay? So what are SCGMMs? All they are is you take your parameter, written like this, as I showed earlier, and just constrain it to be an affine subspace. That's it. It's a very simple idea, right? But it generalizes all the things I said so far. So we came from a completely different direction, and we could have started from the very beginning saying, I love exponential models, I'm going to go to a subspace, and that's the most general model that we get to. But we came the long route to taking 5 years. But that's life. Okay. So what are the model parameters here? So if you look at the parameters, you basically have the transformed mean, and we write it as one long vector. So what we do is we vectorize this precision matrix. So it's a symmetric matrix. You take all the guys who are independent elements in the matrix and write them into as a long vector. So what we do is we say there is a basis B, and then there is basically for every Gaussian an expansion coefficient in that particular basis. And then you'll have a base point for the subspace theta naught, which could be some arbitrary point, as long as it lies on the subspace, because the rest of it, once theta naught is fixed and it's any point in the subspace, these can arrange themselves automatically to model anything in that subspace. So what are the constraints? The constraints are, again, there's just the fact that the dimension is ranging from 1 through this number, which includes the total number of parameters for the means and the covariance put together. Right? But in this setup, there are no such things as means and covariances that you model, remember, because the means and covariance are completely mixed up between all the Gaussians. It's just some basis for these parameters and some coefficients. The only constraint, like I said earlier, is just the fact that P has to be positive definite. So we have two sets of parameters, the tied parameters, which is the basis that's shared by all the Gaussians, and untied parameters, which is a per Gaussian thing. Any questions? OK.
This has nothing to do with the mixture model, just Gaussian so far.
This.
When you generalize that to the Gaussian, does it make the estimation of S, all the A's?
OK, the comment about this is, well, I've focused only on looking at one Gaussian at a time, but really think of it as one giant mixture of all the systems, Gaussians in a system, and each have their priors, pi g, right? So think of a speech recognition model as a single Gaussian mixture. Right? For the estimation purpose, I don't think it doesn't make any difference. So we can view it that way. And then what this is saying is, how do you estimate the basis for the entire system, and how do you estimate each of the Gaussians, all three of the components, the priors and the parameters. It's two, the priors and the parameters lambda, as I mentioned in the earlier case. Right? It's basically these two things. Per Gaussian, you have the prior and the corresponding lambda. Right? The lambda contains all the information relevant to write down the means and the covariances after you do the. Right. So then all the special cases, all the things, so it was a build-up, right? So I just want to show what they are. All the special cases that basically I discussed earlier are special cases where B is block diagonal, meaning you don't mix up the covariance-related dimensions and the mean dimension. They leave them separately. There's no intermingling between the two. Okay? So you have a basis B11 that covers just the means, or the transformed means, right? The size, not the means themselves. And then you have another basis B22 that covers which forms a basis for the precision part. And then, of course, and this is the standard stuff. You write the transform mean and precision basis. So if you look at the different models, the diagonal model says B11 has to be the identity, and B22 has to be this form. Similarly, for MLLT, you have the same thing. EMLT is this, a similar thing. It's all fairly obvious. Precision constraint, use the means to be identity. Now, the last one is this is how we actually, one model which I didn't touch upon so far, which is what we call the subspace precisions and means model. I'm sure some of you may have heard about it or read a paper on it. That's the case where basically it's still block diagonal, but basically the subspaces could be anything for the mean, for the transform means, and anything for the thing, right? That's it. In terms of estimation of this model too, it's very nice, and essentially you first estimate the tied parameters. That's the basis, fixing the untied parameters, and you can show that it's a convex problem. And then you shift out the other one, and then you fix the untied parameters and do the tied parameters, and vice versa.
When you say convex problem, you mean the n step is convex, right?
Correct, right. But overall objective function is not convex, right?
So Ramesh, where does make Van Hoek's work? So it's somewhere between PCGMM and SPAM.
Winston Van Hoek's work basically is it's basically somewhere it's probably somewhere between EMLT and PCGM, in the sense that he has a constraint he forces, which is I have a mixture of inverse covariances, which forces your basis to be positive definite, and you can show that it's an artificial constraint, right? And so that's the basic difference. And I think what happened, my suspicion is, if I look through it historically in terms of how things happen, they saw our work on EMLLT, and they said, oh, we have a rank 1 positive sort of non-negative definite term. Why can't we use an inverse covariance instead as a replacement for that? And that's how that work came about, right? And while we were just doing we're on this program, we marched forward and said next thing to do is this and this and this. But yeah, that's the connection. So that constraint, I think, is artificial. Other than that, I think it's a wonderful piece of work. So it's basically it's very closely related. It's somewhere between these two.
How about Mark-Gale's semi-tight covariance matrix work?
Mark-Gale's stuff would be basically MLLT. It's exactly MLLT. The only difference is, you can do MLLT for the entire system, right? Then it's one linear transformation. What if you do it for groups of Gaussians? That's the only difference. So he has semi-tight covariances, meaning there are groups of Gaussians for which I have an MLLT transformation. But otherwise, it's exactly the same thing.
And how about factor analysis? I think
factor analysis doesn't fit into any of these models. And the reason, it's the wrong approach, because you're modeling the covariance in a subspace, not the precision in a subspace. Okay, so there's nothing like experiments, right? So in fact, way before we started this, actually, after MLLT, before I went in this direction, I actually took a detour. That took me a year. That was factor analysis. And now I'm wised up, and I don't go there. But I go there for a different reason. I'll give you an example. Factor analysis is very useful when you have to model a covariance in a subspace. And that happens not for modeling purposes like this, but for memory efficiency. I'll talk about it later. Let's see how am I doing here. 13 minutes. I should speed up a little bit, but feel free to ask me questions, because I think whatever I cover, I want to cover in a little bit of detail, more so than I can drop things. It's no problem. Any questions? Okay, good. So as far as evaluation goes, basically it's very simple again. So you essentially have this exponent in the in the Gaussian. You evaluate it in this fashion. So effectively, what you have is two parts. You first take a pre-computation. You take your quadratic feature of the x and multiply it by b. That's your basis. That's the first part of the computation shared by all the Gaussians. That's the pre-computation. And then a per Gaussian computation that depends on lambda g, which basically means it's very nice, right? All you do is, if you look at any type of model that you have, the pre-computation part depends on exactly the tied parameters. If you have 20 tied parameters, that's your 20 floating point adds plus multiplies as your computation. Similarly, per Gaussian computation depends on the number of lambdas. So this is your basis-related computation. This is your lambda-related computation. And as you notice, it's just the number of parameters. That's it. So for each model. Okay. Right. So a couple of comments on training that I wanted to make. One is, we trained using both maximal likelihood and discriminative training, but all of the results I'm going to show here right now is for ML. And the idea is to alternatively maximize the tied and untied parameters. Both are convex problems independently, but the total problem is not. The real problem is really the optimization of the untied parameters because, the tied parameters. The untied parameters, it's a per Gaussian thing. So I can take just the data after in the M step, I just take the statistics for that particular Gaussian and deal with it, which is not too bad. But if you take the untied parameters, it's tricky because you take the entire data and make sure that whatever precision you get is positive definite for every one of the Gaussians. If you have 100,000 Gaussians, you better be sure that you do it for all of them. So in other words, if you have 100,000 Gaussians, you have 100,000 of these quadratic eigenvalue problems to solve to make sure that you don't get out of bounds. So obviously, there are a lot of tricks to make this happen, and we do it. And they're in the papers. It's all clearly described, so you can actually exploit them if you want to play with these things. And of course, we use quasi-Newton search methods. And the line search, we have to have a version of the quasi-Newton search method which allows you to specify bounds in a line search, because otherwise you go out of bounds. So there is such a package that we use, and it's a public domain thing, and we just add what we need to make this happen. Okay. Yeah.
You still constrain your predictive training?
Yes.
Why?
The reason why we do that is because at the end of the process, we are going to use a code that is used for Gaussians. And therefore, you compute the determinant. So you don't, right. So, well, it doesn't affect us at the time of training because in some sense it's irrelevant, but
it is just, if you had a different implementation, you wouldn't care, right? You only care about the stereo.
I need to think about it a little bit carefully because really what, ultimately at the end of the process, even with discriminative training, we are building a Gaussian mixture model, which by definition means I need to make sure precisions are positive. Right? If I say, look, I don't care about Gaussians, I'll use those features that you saw there, but I'm not interested in having a Gaussian, meaning that k of theta, which is your constant, doesn't matter. Then I may be able to get away with it and discriminate, right? But as long as I say I have a Gaussian mixture model, then I'm forced to make sure, yeah.
As long as what I was saying, if you say that you have an exponential model with these features, and I'm just going to train it using these techniques,
then it's fair game, but we have not done that. What we have done for discriminative training is assume it's a Gaussian, I will train a discriminative model. Okay, that's what we have done.
Just make sure. So discriminative training applied to this model hasn't been published yet.
It'll appear, I think, in 3 months. It got accepted.
2 papers with me.
That's right. The first paper appeared last month. The second paper will appear in 3 months.
Okay.
Yeah, and that has the discriminative.
Contains the
Correct. Yeah.
Okay.
Right. It does. So the experimental setup, okay. So all of this work, my colleagues in this work, we're all people. We are all interested in, helping our speech recognition product for both, Alex mentioned on the client side, which is embedded in a car as well as in telephony. The bulk of this work was done in the context of the car experiments, and a lot of, So that's the context in which we ran the work. So basically, to give you an idea of what we used, it was a subset of that training corpus, 500 hours of data, and the test set is fairly large, 75,000 words, so that we wanted to be sure that whatever we run, we believe in the results. It's a small system, meaning 10,000 Gaussians and 680 states. The way we computed the features is we compute 13-dimensional capsule features and then attach or splice 9 of them together to make 117-dimensional features and then project it down to whatever dimension we want. And we tried a bunch of dimensions to make sure these results hold regardless of the dimension of your target feature space. And that could be any number. So we use LDA for that.
Question?
Yeah.
Is this for English?
This is US English.
Why are there so many forms?
That's a very good question. It's basically because we used special phonemes for digits so that effectively we had a word model for digits to get better performance. It's just a trick. Very good question, yes. Yeah, we don't have, it's not like we have invented a new version of English with more phonemes, no. Okay, so results. Results basically, y-axis is word error rate, x-axis is the dimension of the final feature space. Remember I said you have an LDA. We tried a variety of sizes all the way from 20 to about 100 and, 12 or whatever that is. And what you see is three curves. The first curve is the performance word error rate of a diagonal covariance system using MLLT. The plain vanilla diagonal covariance system will be much worse. It'll be somewhere here, let's say, okay, that I've not shown. So I've used this as the baseline. Then I've shown a precision constraint GMM which has exactly the same number of parameters per Gaussian, which means computation is roughly the same per Gaussian, because that's the bulk of the computation. So these two curves are basically exactly the same computation. And the third curve at the bottom is the full covariance, which obviously has significantly more computation than a diagonal covariance. And the main point is if you take a typical size, like 52 dimensional, which is a typical size close to what most people run in the 50 dimension is typically 50 for most speech recognition, or 39 to 50, whatever that is. You notice that a bulk of the difference between full covariance and diagonal we just completely cover with this model, right? And the cost is exactly the same. So you get full covariance performance nearly at diagonal covariance cost. Okay, and the gain is also uniform across all dimensions, which is a very nice result, saying that this is a very stable thing. It works regardless of your dimension. The second thing is to look at how well does. Now, there are two ways I said we can approach full covariance. One is you can approach with these rank 1 bases. The other is you can approach with the full bases, the SKs. Well, how does it look in terms of performance, right? So, as you increase the dimension from the feature space dimension all the way up to the maximum, which is the full dimension for a covariance of that dimension, you notice that at the extreme case, obviously, they're both modeling full covariance, so you should get the same number. But as you have fewer and fewer parameters per Gaussian, you notice that the EMLT model performs significantly worse than a precision constraint GMM. So the point is, if you say that I cannot afford too many parameters, then it makes more sense to use a precision constraint GMM, right? And there is an additional technique which I'm not going to talk about much in this talk, which basically we build PCGMMs, but under the covers we use an EMLT-like structure. And the reason, in other words, what we do is we say each base is SK is itself a sum of rank 1 terms added up, where the rank 1 terms are significantly large, not D, but some number. And this is what we call a hybrid sort of EMLT PCGMM model. And the reason for doing that is, I don't know if you guys caught this comment I made a while back. EMLT has an advantage at test time too. Computationally, it has an advantage because it's like evaluating a bunch of diagonal Gaussians. This guy has the accuracy advantage. So that's why we came with the hybrid, which is a combination of both.
So but if you just do the full correlation matrix training to begin with, completely separate system without using all this approximation, then do you get identical number, 1.56?
1.58, correct. Yeah.
In that case, I mean, you have to go through all the estimation process.
If I use in this code, we ran through the estimation process. In reality, you do nothing, right?
So that means approximation is exact.
Oh, this is exact. So if you
identical,
right, you get exactly the same results, right? In this one, you do the optimization, but full covariance, you don't have to do anything, right? Okay. The other thing I wanted to mention is, okay, let's compare all of them, against each other from the point of view of, performance, right? So earlier I showed performance going large dimensions, meaning from D, feature space dimension, all the way up to close to the full covariance dimension. What if I focus on dimensions that are much smaller than the feature space? That, by the way, we can never do with our standard methods, because for means, you need, if you have 50 dimensions, you need 50 numbers for the means, and then you work on the covariances, right? So you have typically large numbers. Here, the feature space is 52 dimensional, but we're only using 16 parameters. So obviously, you cannot have an LDA plus MLT model, clearly. Precision constraint GMM, I don't know why we didn't have. Oh, yeah, we didn't, because the mean has to be modeled separately, so you cannot have this number. If you use a subspace for means and precision separately, and say each has, mean has, I don't know how many parameters, and maybe in these experiments, what we did is we ran a sequence of experiments to find out how much we should give to the mean and how much to the precision to get the best number. Okay, so this is your SPAM model, and this is your final SCGMM number. So with 16 parameters per Gaussian, you get this sort of performance. Then the same thing with 26 and so on and so forth. So every row has basically roughly the same number of computation because it's the same number of parameters. What is interesting to see is if you take a standard MLT system for this data, you get a 2.7 word error rate. You can get the same sort of performance with just 26 parameters if you use SCGMM. So point is basically you can get close to the best diagonal number by using very few parameters.
Why can't you map the features down to 16 dimensions using LDA and then run the baseline?
you can do that too.
Throw away information.
That's right. You can do that, but the performance of that is much worse typically. I don't, we don't have the number here. Yeah. Okay. The other question is, the entire discussion so far is fix the number of Gaussians. Let's play with the parameter and see what we can do. Then, the obvious question somebody might want to ask is, what happens if I increase the number of Gaussians? I have that luxury with diagonal covariance, very cheap. Let me have 600,000 Gaussians. And in principle, in theory, enough diagonal Gaussians can model any distribution. Therefore, you're done. But in practice, I don't think it's the case. At least we find it's not the case. So we increase the number of Gaussians, and since we have finite hours, it could support up to easily 600,000 Gaussians, no problem. Here's the diagonal covariance, the MLLT model word error rate. It keeps improving. It still is improving. It's not saturated 100%, but maybe we can go a little bit further. But let's look at the full covariance side. With 5,000 Gaussians, things were okay. 10,000, that's the number we use for most of our experiments. Around 40,000, we are getting the best number, and beyond that, we start hurting, right? So the point is basically full covariance. Essentially, you very quickly run out of data. Right? And so the interesting thing is if you look at these two numbers, the 1.5 and 1.65, you get basically, and if you look at the total number of parameters, building large diagonal models is extremely inefficient is the point I'm trying to make. You can do much better by modeling a full covariance with much less number of Gaussians. If that is the case, all the things I mentioned earlier of doing the full covariance in a smarter fashion, which is what that was all about, makes sense too. Right? So that is to just make precisely that point that we generated this number. Okay. So that's all I'm going to talk in terms of modeling with Gaussian mixtures. And then I want to spend maybe 5 minutes on this one additional idea in modeling and then focus on adaptation for 10 minutes, and that will be the end of the talk. OK, so here's the idea here. We said, OK, we can model with Gaussian mixtures. Great. Now, what if we do an additional twist? We will nonlinearly transform the features first, and after that, do exactly what I described so far. Right? So you have an additional degree of freedom. Which means basically you have to deal with the likelihood in the, what you care about is the likelihood in the original feature space. That's the likelihood in this transformed space times the determinant of the Jacobian determinant, which is an ugly thing to carry through if you want to do ML estimation. But nevertheless, if you want to do an ML estimation, in principle you can use generalized EM, meaning I do standard stuff on the Gaussian part, fixing the nonlinear transformation. Once I'm done with that, I fix everything here and try to do the nonlinear transformation. In principle, it's possible. But in practice, if you want to do it, first of all, you might want to restrict the Jacobian to be one uniformly, meaning only deal with volume-preserving nonlinear transformations. If that's the case, you can write down the Q function for optimizing the H, which is the nonlinear transformation. You can write it in this fashion. And it should look sort of obvious to people who are familiar with Gaussians. Right? All it is a weighted sum. This is basically the likelihood of the data after the nonlinear transformation. And that's a function of the nonlinear transformation because the sample covariance depends on nonlinear transformation. So you have to maximize this thing with respect to H. So that's the idea. So what we did is to restrict the transformation such that it has this structure. It got some sort of a lower triangular structure. In fact, precisely speaking, the Jacobian is lower triangular. We enforced it by doing this sort of constraint. So the first one will be just the first dimension as the second one will be the second dimension plus some function of the first dimension, and so on and so forth. Additionally, in order to be able to run some experiments, we decided to restrict H to be in the quadratic affine family. First of all, in the affine family, and this is required because once you go to these nonlinear things, you have to figure out if you have sufficient statistics to estimate the parameters. You only have them if you're in the affine family, meaning the parameters appear linearly. Second thing is we chose the quadratic family because that's the first simple nonlinearity we can deal with. So basically, each of these functions use, which kind of are related to the H, are of this form. And so the parameters of this nonlinear transformation are these coefficients, the A, M, and J. And because once you have this sort of structure, you're forced, the results depend on what is the ordering of the variables, right? So to overcome that, we said, I'm going to allow ourselves a little more freedom. We can allow our data to be transformed by matrix linear transformation. In particular, if a permutation is included, then obviously, right, that's the idea. And then we said we'll have a linear transformation after it too, because nonlinearities, so you want to do things we always do, which is linear transformation before and after. Results. We were quite disappointed, actually. For all the hard work that went into this is very disappointing. But nevertheless, the results are interesting. I mean, So if you take, so the model is full covariance, diagonal, or MLT. This is after the transformation. The nature of the transform itself, the number of Gaussians, right? So the nature of the transformation here, if you look at, this is just the quadratic followed by linear, linear followed by quadratic transformation. And this is what you get, slight degradations. At different dimensions we tried from the LDA, slight degradation too. If you go to something like a diagonal model, we found some small gains. In fact, we found a reasonable gain after throwing in this additional linear transformation. But then if you go to the bottom one with MLLT, basically the gains again between these two the differences are small. So in other words, the bulk of the gain we got here, from here to here, seems to have been due to the A matrix, not the nonlinearity, which is what I meant by we're sort of disappointed with the results. Okay, so this is the sort of results we get. But nevertheless, I think this whole idea of using a nonlinear transformation in some fashion before doing GMM modeling is a flexibility we want to exploit. I don't see anybody has been able to get to work. People have tried, but at least people have tried in a very principled fashion is all I would say. And this we thought we were doing it in a principled fashion, but not good enough.
But do you think the problem here is that when you try to figure out the right nonlinearity, you should somehow put this posterior probabilities concept into the nonlinear transformation rather than just doing x squared or something?
Oh, okay.
Do you think this is an issue there?
I don't know. We actually don't know. We want it right. I don't know. The other thing that I wanted to mention, so think of it slightly differently. After all this nonlinear transformation, you can also view this slightly differently as an interpretation. I just wanted to make the point, which is here you're having a mixture of distributions where each distribution is an exponential with on the exponent you have fourth order powers. Because you had a Gaussian, the features themselves were quadratically transformed, so it's like fourth powers. So it's like some funny way of having a distribution of the exponential family with fourth powers. And all this, Jacobian determinant, restriction, this and that we did just to get to this. Ultimately, that's what we get. And naturally, you cannot put restrictions because if you have fourth power, how do you make sure it integrates and it doesn't, it converges, right? All these issues are there. So this is a nice way of handling it, but nevertheless, not good enough for speech recognition yet.
So if you use a somewhat more complex nonlinear function, like neural network, that kind of nonlinear function, is that going to fit into this mathematics? You
could. The use could be any general function, but as long as, like I mentioned, the parameters appear in an affine fashion, you will have sufficient statistics and you can estimate it. But the statistics themselves could be very complicated. To do this thing, the statistics that we had to do was very complicated because we had to have fourth order terms, xi, xj, xk, xl. So try writing code in an efficient fashion for these fourth and higher order things because there are too many symmetries. Just two will have this standard diagonal symmetry, right?
So if you want to use the Nelson Morgan type of neural network as a front end, you probably will be able to carry out.
Yeah, I don't know how we'll be able to carry out. Yeah. Yes.
All these results are on CFG small vocabulary, right?
They are all on small vocabulary. I don't know, and this chart will tell you why too. So we ran another set of experiments where we said we'll have per state a nonlinear transformation. Why have one global per state? We did those experiments. To build such a system, we actually had to reduce the number of Gaussians in the system to 1 per state. I mean, it's an expensive experiment to do these things. There we found that, okay, this nonlinearity helps. But remember, we have killed our baseline to 6% and we got an improvement. So it's not a big deal. It's not something to write home to mom about. But nevertheless, the point I'm making is we were trying to explore to see why didn't we get it to work? And we find that it does work if you have multiple transformations per, say, a state or groups of Gaussians. Same with the full covariance case. Basically, this is 10,000 Gaussians. And this is a per state thing. And here, I think the gains were smaller or non-existent. Anyway, the main point here was to say that this is a direction that needs exploration. We don't have great results yet.
As far as the error metric is concerned, I mean, the word error is nice, but I would assume that there's a more user-centric thing. Like, you probably want to accomplish something.
Task completion, whatever, yeah. Go on.
So, does any of these make the difference if you look in those terms?
You mean the gains that we're getting?
From 3 to 1.5% were the error rate reduction. Do you see any improvement in task completion error rate?
It's a good question. I don't know the answer to it. It depends on the application. And most people in this business are aware of this issue, right? But, so what I've taken as a view, let's focus on just word error rate and say what's the best we can do. And it's possible that a lot of these techniques, from the end user perspective, depending on the application, may make no difference. But that's the nature of the speech recognition business, right? Improvements are hard to come by, so you come right. So I don't know what else to say. I mean, that's the nature of our business.
Back to this discriminative feature transformation work. You mentioned offhand that no one has been able to really get it to work well. This idea of nonlinear feature transformation.
Right.
Would you not put Popey's FMPE into the same class of algorithms? Or the discriminative splice training that we've been doing here? Or would you say that they aren't successful?
Okay, maybe I'll modify it to say maximum likelihood.
Okay.
Yeah. Discriminative, I understand, what you're saying, but those results I'm happy with, but not fully satisfied. I think there are multiple teams scratching the surface on this problem, but nonlinearity in the front end, if you can do it in a smart fashion, I think you can get big gains.
Right.
That's all I'm saying. But I have no proof because I didn't get any good numbers too. But yeah, those are good results. Povey's result, the probabilistic optimal filtering, splice, all these are, but they come from a different approach though. Anyway, what I'm looking for is a single nonlinear transformation that works uniformly, while those are all approaches that take a certain feature space, quantize it, if you will, crudely speaking, to regions, and in each region you do some sort of linear transformation,
right? Which
is the basic principle there. Okay. Yeah. So anyway, right. So now I want to switch to adaptation. Is it a sharp cutoff at 11:30?
No, we have the room until 12. Actually.
Okay. So I may take a couple of minutes extra if that's okay by you guys. Okay. So in adaptation, basically, as everybody knows, it's a mismatch between training and test. And there are two approaches. Either you adapt the model or you adapt the features. So I'm just going to exclusively focus on adapting the features. And I'll talk about two things. One is a small subtopic, which is, for those who are already familiar with it, it may not be a big deal. But basically, ML estimation of AB, people do standard FMLLR, which is feature space maximal likelihood linear regression. The issue with it is basically if you don't have a few tens of seconds of data, this thing won't work. So in other words, if you have a telephone call and you have one utterance with 2 seconds, this thing you can guarantee it will not work. Then you can try tricks like block diagonal, this and that. It may work, it may not work. It's a tricky issue. So we were trying to see if we can solve it once and for all in one clean fashion. So what do? If you have a hammer, you keep hammering everything away, right? So that's the same thing. The first thing we tried was we said, look, we have this transformation we're going to estimate. We may not have enough data. What do? We'll expand it in a subspace. How do you get the subspace basis? You look at training data, each speaker computer transformation. We did that. It works quite well. We actually wrote a bunch of papers on this too. Until we realized, one day that maybe we should not try to force the subspace constraint. Why don't we just use a prior? Such a simple idea. We tried that, and guess what? It did much, much better than this. Okay? And so it depends on what we use for the prior, though. So what we did is we said we're going to use a sort of a map estimation of the regression matrix for feature space MLLR. I think others may have also done this, but I'm not on top of the literature in this space. So this is what we did. So what we did here was basically we said that we're going to have a prior on the linear transformation and a single Gaussian prior, which means a mean and a covariance. So remember, the covariance is d to the 4th dimension now because you're having a covariance for the A matrix. So we had to do something about it, and that's where we use factor analysis. That's a classic case where you have a covariance to compress and store somewhere. What do? You use factor analysis. So what we did is we actually did factor analysis to just store these guys. So there's no ML estimation, nothing. It's just basically, well, actually we did estimate in ML fashion, but the point I'm making is this is not to model the thing. It's more for compression we use this trick. We could have used the precision too, but I think this is what we tried first, and we just stuck to it because it works well. Okay. So what happens with this technique, right? So again, remember, there's no block diagonal constraints on this. All we do is we have so we have a baseline number. This is on some telephony test set. I don't recall which one. The baseline is at about 10.7 seconds. The average session length for this adaptation was about 8 seconds. And then if you use standard FMLLR, you get a gain. Because 8 seconds, by the time you start seeing gains, 2-3 seconds is when you have problems. So this is like 3 utterances or 2 utterances. Then if you go to FMAPLR with just D factors, it's not a whole lot of storage, you get to this gain.
You train the prior on the training set?
The prior is trained on the training set. So we imagine if you have 1,000 speakers, you have 1,000 examples of the A matrices. And we basically just drop it down by factoring out to say D, which is 50 in this case, factors. OK, this one I'm very excited by. So let me spend a few minutes on this one, which is adaptation of the front end. Right? And we have done a couple, published a couple of papers in this area, but we have not labeled it nicely, so people may not even see the connection between the two, unfortunately. This is one thing I've learned over the years, and if you don't have a good name for something, people don't even connect it because, but anyway, we have not done it yet, so we'll have to figure it. That's what I was telling Karthik the other day. Unless you label it and brand it, this is going to be lost in the literature, but anyway, we'll see. But it's a very neat idea. The idea is you have the acoustic features. What the signal processing does is it goes through a sequence of stages, and finally you get your final feature. Each stage has its own parameters and its own inputs, right? That's the typical setup. So if we have something that we optimize, minimize some criterion, and that means this could be negative log likelihood, for example, over the parameters of the front end with the fixed model. So the model is fixed. All I'm going to change is x of theta. And I'll use the thetas from these different stages in such a fashion that I do something useful. So what are the choices of objective function, right? You can clearly the first choice that comes up is maximum likelihood. Okay, but unfortunately it's not a good thing to use because maximum likelihood assumes you need to do this Jacobian thing that you carry around all over the place. And if it's not invertible, then if you like an LDA transformation, how are you going to train an LDA? Because that's a projection. You can't deal with projections in a likelihood framework. And then there are other things like Melboning, a whole lot of things we do in the front end that basically cannot be viewed as dimension preserving or invertible. Second approach is you could use MMI, some discriminative training approach. But unfortunately, with discriminative training approach, the issue is, can you do discriminative training in an unsupervised fashion? I personally think it's a very dubious thing to do, because what are you discriminating against? From what are you discriminating from what? Big question. So the unsupervised adaptation, which is what we were thinking of in this context, like you're thinking of automotive situation or in a car or in a telephone situation. You want to do unsupervised adaptation. So
it's okay, but since your error rate is so low, you just run second path.
Yeah, but think of...
If you get 98% accuracy, then you just treat that as if it's...
But see, okay, we should talk offline about this because as a criterion, it's dubious. This is a longer discussion. It's a bit philosophical too, but nevertheless, I can try to argue to you that it's a bad idea. So anyway, I don't want to go there now. The thing that we did, okay, which was basically to say, look, we cannot do likelihood because Jacobians are involved, but can we do something that's close? So we said, we look at the model and see how much our likelihood improves over and above using a very crude single Gaussian model for the data. So that's this. And I'll just show the equation so it's much cleaner to see exactly what we did. So we first consider the ML objective function, which is negative log likelihood, and then the Jacobian term. And then we want to maximize with respect to the parameters which are all sitting in this x, right? The second approach is MMI, where you have some numerator lattice which corresponds to the correct hypothesis, and a denominator lattice that corresponds to all the hypotheses, including the correct one and the competing ones, and you use this sort of criterion. But here, like I said, we need to know the correct hypothesis, this guy, in order to be able to do a kosher experiment. The third idea was you use the likelihood term, and you penalize it with something that looks like this. 1/2 number of samples log determinant of the total covariance of the adaptation data. So this, it's not hard to see. This is like saying, I'm going to look at the likelihood of the entire adaptation data with a single Gaussian model. And then you say, whatever model I choose must have an improved likelihood on top of this by a certain amount. And you maximize that difference. And that's what this does. But with this, you can deal with any part of the front end. That's the real reason why we went with it. The criterion allows you to adapt anything. So how did we optimize objective function? We used, like in all the other things we did, limited memory BFGS, which requires basically the function and the gradient. And the good thing about this is, since we said it's a composition of functions, we can use backpropagation exactly like people do in neural networks. So essentially, all you do is every stage in the signal processing pipeline needs to compute basically the gradient of that stage with respect to its input and with respect to the parameters of that stage. And the parameters of the stage, it could be, depending on what you're doing, could be different things. Like, for example, I want to optimize the Kepstrel matrix. The DCT is your parameters. I want to change the log. Then, you replace log with a parametric family, and then the log is one of them, and then you do that. So that's the basic principle we followed. Okay, and this I already touched upon. The good thing about the whole thing is it's very modular implementation. We just go to wherever we are doing computations, add this extra gradient computation, and add this maybe log that Jacobian computation, and you're done.
So in this case, if you want to look at the frequency scale, window, how to place the window, do you consider maybe the central frequency versus the edge of the frequency as part of the parameter?
You could do that. You could. It's flexible. It does.
But if you do the derivative, how can you find the gradient on that?
Gradient of which one? You're talking about the windowing?
On the window.
We have not done that actually.
Not smooth function.
Yeah, it has to be a smooth function. Otherwise, what we are saying will not work. In fact, we did a few tricks. Like for example, spectral subtraction is a piecewise constant function, right? So we have an analytical approximation to it, which is in a parametric family that in the extreme limit allows you to approach standard spectral subtraction, and we showed ways to improve it. So I'm sure we can, we have not thought of it, but I'm sure we can, if you have a discontinuity, you replace it by some smoothness, have a parameter in the limit goes to this ugly function, you're in good shape. So we can handle it, I'm pretty sure. So anyway, so this is basically to say that it's very modular. Okay, so these are some results on just the first. Let's look at linear transformations. Okay, so this is a car database again. This is the baseline word error rate. And we picked one of the spam models just to make the point that all the stuff that I'm doing we can do with any of the models I discussed earlier. This is one that we picked. On the maximum likelihood side, it's when you do an estimate in AX plus B at the end of the pipeline, this is exactly FMLLR, and this is what you get. This is the number you get. If you use MMI on the same data, you actually already see with 20. This is with, I don't know, yeah, 25 utterances is correct. Basically, it overtrains. Even with 25 utterances, discriminative training with supervision, with 25 utterances, screwed up here. So that's why I'm not a fan of discriminative MMI for this sort of stuff. This is a hybrid criterion I didn't really talk about, which is a mixture of ML and MMI, because once you have these criteria, I can say alpha times this plus beta times that. And this is showing that if you have some flexibility, you can get gains. But the neatest thing on this whole thing is, instead of doing linear transformations after the LDA, why don't we do it on the 13-dimensional Kepstra? Yeah, you can do it in a maximum likelihood fashion because that's followed by splicing and LDA and all that. So we use the last criterion that I said, this what I call GMMI, approximate MMI, as I call it, right? With that criterion, we basically built and we showed that there's significant actually gain at 2 utterances by going to this, doing the adaptation before rather than after the LDA. Yeah, and in case you're wondering, I have numbers in the backup. I didn't want to confuse the issue. If you you can do other things on the FMLR like block diagonal and stuff like that. Those numbers are all worse than 1.67. They're like 1.8 and 1.9 and stuff like that, right? And as the number of adaptation utterances goes to in the extreme case, they're both performing equally well. Which is another good thing. If you use block diagonal and stuff like that, by the time you go to the full number of utterances, you've constrained yourself.
But LDA, huddle parameter,
okay, so
it's going to be optimized there. You started from waveform to begin with.
Yeah. So in each case, in this particular case, in the entire signal processing pipeline, I only optimize one thing, and that is the matrix. Put in a matrix after the Kepstra. You can optimize multiple things. The examples I've given now is just one. Either I can use an FMLLR, or I can use a transformation before the LDA, before or after the LDA, and before is better than after, right? The other thing we can do, examples like this, right? I can do LDA adaptation, which is exactly what you're saying. Why don't I take my LDA and just replace it with an updated one? You can do that. Again, you can't use likelihood. You can use this criterion. If you do that, this is what you get. This is a slightly different system, so the baselines are different. If you do FMLR, you get this performance, but if you use LDA adaptation on top of FMLR, you get this performance. Okay. Similarly, we took spectral subtraction, and created some sort of a parametric approximation to spectral subtraction that basically has some parameters, one parameter per dimension. We took that and we did the same thing, and said let's optimize this parameter, and we got a significant gain actually. Right. That's the neat thing about it. You can pick any stage in the pipeline and do this. We did similar things with the power law compression instead of log, power law, other things. The differences are too small, so I'm not reporting numbers. Same with mel binning we tried. We didn't get much improvement of what we normally do. DCT is another thing we can play with.
Did you do FFT?
FFT we did not. Definitely not. Yeah, because then we had to do it, again, in our system we use the magnitude followed by f15, not the squared magnitude. It's not analytical, so we didn't go there. But it's a possibility to get there too. So that's basically all I wanted to talk about. So this is basically the summary of what I try to cover today. So there are two topics I talked about. One is modeling. This is Gaussian mixture modeling. And the main message here is that you want to work with the precisions and the precision matrices and the transformed means of the Gaussians, which are the natural parameters and exponential family. It's found beneficial in multiple ways for both computational storage as well as robust estimation reasons. And what we have is a very flexible family, that has some specializations. Each of them have their pluses and minuses depending on the amount of data you have, what is the number of parameters you can throw at it, how much you care about efficiency, and all those. You can pick the right one that suits you, and it suits your needs. The other point I wanted to make is, let's not forget that if you have enough data and you're at a point where full covariance doesn't overtrain, and you want to build a system quickly to make sure it works and gives reasonable results, you shouldn't go for full covariance. And then you can start the strip at your leisure when you think you can start making things more efficient. The other part is adaptation, basically, where you can do very quick adaptation without screwing things up by using a simple Gaussian prior using a factor analysis. That seems to work quite well for us, and it works with even 1 or 2 seconds of data. You never run into trouble, and you don't have to put in all these artificial restrictions like block diagonal, and stuff like that on the matrices. The other one is, which is quite exciting. We've just started exploring this, but I think this is fundamentally a nice way of optimizing the front-end parameters. And I just gave you one example of a criterion that we use using this total covariance as the normalization. That's just as ugly a hack as anything you can think of, at some level. So you may want to come up with brighter ways to handle that, because that, I think, is an unexplored area, this whole thing of optimizing the front end. That's basically it. I'm done. Thanks for listening.
Thank you. So we have time for questions.
So I had my PhD student a few years ago doing something very similar to the last one you are doing, namely optimizing the DCT transformation. In other words, making that not as fixed, but making it as it turns out that the result has a slight improvement over the DCT, but it has to be obtained from with the initialization of DCT.
Well, you start with DCT
and other initialization won't make it work.
Yeah, I have some numbers actually, but the numbers, they're very weak. I think I remember putting it in this list maybe. Yeah, see, look at that. So we tried DCT. I do remember this. It was
This is very good.
This is what we have, a minor gain with DCT, right? 17. So I didn't want to stress that, so I didn't put it up. It's like a small gain. Root compression also gives a small gain from, right? Mel binning did not give us any gain, basically. And some of them we actually ran MMI too, by the way. But it gives them. Yeah, so I'm not, What I was confident we are getting gains by, I just wanted to stress. This is like, these are results.
So do you get the impression doing all this just perturbation of whatever existing technique that we have so far? Or do you think that?
It could, okay. The question is could it be in the noise? I don't know, but the only thing I have going for me is these are numbers. If you say a small change, each test set that we're running it on is about 75,000 words. So think of it as 100,000 words. So if you have 1%, you have 1,000 words. That's a big number in difference in performance, right? So these are, I think they are significant if you see numbers in the first decimal place. I really believe it. Second decimal, okay, it's a little harder. In all of the cases, since we are generalizing, okay, so this is a principle I always follow, and I think it's at some point I'm going to pay for it, which is regardless of what I do, when I go to my next bigger model, I will make sure that when I generalize something, I'll make sure that the previous model is in the family, and I'll make sure I initialize it with the previous one. Every experiment you heard today has followed that principle pretty much uniformly, which means there may be some smart thing. Yeah, I could be stuck in some place. But then I found that it's such a complicated problem in speech recognition. I can be I can be a cowboy and go about shooting all over the place. But I think I'd rather be conservative and really make sure I improve. So that's a philosophy that a lot of people don't agree with me, but anyway, we have followed that principle.
Can you give us a little bit more details about the parameters you use to optimize the spectral subtraction, the front end?
Okay, so I did not do the work myself, so I may not do justice to it, but I'll give you a rough idea. I know graphically what it is. So basically, in spectral subtraction, my understanding is essentially, so you have some function that looks like this. So beyond a point, it's straight linear. It's like, what you observe minus, the noise. And then at some point, there is a threshold where basically you use noise. So it looks something like this. So what we did is we said we're going to have some family of functions which basically will, it looks something like this. Okay? And depending on a parameter alpha, this will hug it closely or be away from it. I see. And we said, let's optimize this parameter. That's the basic idea. So it's a very intuitive thing. It's not based on any theory. We just said, we know this works. Can I improve this thing? It's the same principle. I'll start with something that's close to it and try it out. And it seems to work.
So another high-level question is that, would it be fair to say that if you have a very large amount of data, 2,000 hours of speech learning kind of years kind of framework, then any of the things earlier on in terms of the Gaussian covariance
modeling, right?
It's not going to be of direct use.
Actually, no.
Unless you train all coverage metrics in the full coverage metrics.
Yeah, but I can assure you the full covariance guys are very data hungry. You will run out of data sooner or later. So you're guaranteed basically that having this framework you can do much better. And this is proved. It's an unfortunate fact of life that this was proved by guys in Cambridge on large vocabulary, not at IBM, but that's life. Yeah, because those guys worked on it and got it to work. So the thing is, like I said, the focus of my team is on products, and so we have not looked at that problem. I've not touched large vocabulary since 1999, actually. So it's been a while.
So I suppose, one of the three things that you I think just did for the top of the years for last year evaluation. One of them is full coverage metrics.
Correct. So what? Okay.
Didn't try your stuff just to see whether.
Correct. So that's because of evaluation and timing consideration. In fact, he knows this. I've told him enough times. What you have done is you build the biggest full covariance you could build, right? Now, I can build a larger model that can use this stuff, which you cannot have full covariance for, that I can guarantee will be better performance than its full covariance. That I've told him many times, but we never, right? It's a question of time, but I believe that. So this is so flexible. You have so much control, and full covariance is in there. You cannot go wrong, right? Why do you have to pick a boundary when you have the entire spectrum of things, and you try it, and whatever works best for you, you use. One disadvantage is because there is such a big family to look over, it's daunting in some sense. But that, you have to play on enough data sets to get the gut feeling. So that's another thing, If somebody, for example, who had done this work, like, a Peter or a Karthik or myself, had spent the time, we have enough intuition to say, try this and try that. So I do agree. We opened up a bunch of possibilities, and so which correct combination you choose, that you have to learn by experience.
Yeah, I think another advantage of this is that even if you have a large amount of data, those data may not be sort of transcribed correctly.
That's right.
In that case, you probably can win by doing this.
In an unsupervised fashion, you're saying, right? Yeah, we have not done these models in an unsupervised setting. We've done some experiments, but they were largely focused on that problem. Therefore, we did it with diagonal models. So I don't know what might happen.
But computation-wise, which one is more efficient?
Which one? Between full covariance and this? Oh, this is much more efficient.
Well, but many people actually do a lot of tricks for doing, time. You have different types.
Good. Okay. So once you build a model, right, you can then say, look, at computation time for a product consideration, I'm going to quantize things. Right? I have to quantize my model. My Gaussians will be quantized. That entire trip you can carry in this case. There's nothing that stops you from doing it, and it works just fine. So this is complement. We are focused on the modeling stage. At the very end, you will, of course, do all those things. But, it's not precluded, right?
About the separate mean and the precision matrix. Maybe assign different dimensions for this combination.
Yeah, actually some of the numbers did have that. So this model, which I call SPAM, is exactly that. Subspace, precisions, and means, where you have a different subspace for the mean, different subspace for the precision. Each can have different number of parameters. And the numbers I showed are the ones where so then you have a choice, right? You can scan. If I say I have 26 parameters, I can use 1 for the mean and 25 for the precision, or 10 for the mean, 15 for the precision. So we scan that entire thing, to get that one number that's sitting there, to show that even with the best number, that's what you get. So, actually, the experiments behind all those numbers are fairly huge. Even though the data set is small, the number of Gaussians is small, it pretty much, by some estimate that I had, it's probably is about 50 years or something of compute power on a single machine or something like that. Yeah, so it is an obnoxious number.
So another thing is that this is your sort of internal data evaluation, right?
That's right.
So it would be really nice to put them into either timid or maybe some digit or something like that.
Yeah, I agree with you. That's right. I agree with you. We have not done any experiments on publicly available database. Actually, that's not true. Let me take it back. Large vocabulary, we did these experiments on switchboard ourselves and showed improvements. It's just that the years team did not use it in the evaluation, but we have shown results. But that was not using SCGMMs, it was using SPAM, because that was the model we had at that time. That was 2 years ago. Additionally, Cambridge has shown results, and they use it in their evaluation system. So it works on large vocabulary that we know, and others have tried it on other data sets. But we ourselves have not done it on a variety of standard test sets similar to this small vocabulary like timid and stuff. We have not done that. But I'm convinced that this works, and it's been tried out by other people. That's the best. There's no proof other than having somebody at Cambridge try it and tell you it works for me, right? So, and you may not have found it out. You may not have enough to do a rich set of experiments. We wanted to use this because we have control. We know we can try all the different possibilities. We wanted to, it's in terms of exploration, it was a great database.
Also, you mentioned the image processing.
That's MLLT. Okay, this was in handwriting recognition. This was like in 1998 or 9. I was working with somebody in the handwriting team, and they were using HMMs. I said, if you're using HMMs, you're using diagonal covariance, you better use this thing. And so they just gave me a bunch of covariances. I gave them a transformation. They went and used it, and it worked just fine. Okay, so I knew nothing about their data. All I know is, here's some covariances, here's my matrix, go work with it, and it worked fine. They were very happy with it, actually. Speaker ID was another shocker. They had 50% improvement in performance.
So who did that work?
So they wrote papers, and I was a co-author and everything. It's great. I don't have to do anything now. Yeah.
The speech recognition, we have a number of non-distortion factors, background noise, channel, speakers, and what you have been, talking about is basically using generic, transformations, sharing to cover, collectively all these factors. On the other hand, there are also, for example, modeling noise or channel, is only one bias in the, appropriate domain. Channel, for example, MFCC domain is, random vector. What is your thought about, trying to model individually all these, factors that are, essentially very simple in the original program space? For example, a simple additive background noise, it requires only one power spectrum, component to model that. But if you model this in each of Gaussian states, you may have a state-dependent bias to cover that kind of complex. After all the processing stage, it becomes very complex and requires a huge number of parameters to model.
So I agree with you, basically, and my reaction is we should do both. So the first part, modeling, was all purely, if you notice, data-driven approaches. On the final feature space, we do whatever we can. But the adaptation was very different. We actually looked at the phenomenon, which is spectral subtraction. We said, let's try it. But then whatever way you model it, you don't know how to model it perfectly, so you do whatever you can. So that's why we said we should give enough flexibility and let data decide. So I believe in doing these knowledge-driven approaches also, but most of them happen in the signal processing pipeline. But once you get to the features, the rest of it is straight statistical modeling. And there, all the things that I said in the first part of the talk are relevant. And also to make a point, the entire first part, all the models we discussed, the basic Kepstrel features did include spectral subtraction in them. Because this is the car database, and as I showed you, the results were over data at 3 different speeds. So we had to make sure we do something for noise, and that was done under the covers. So we always did spectral subtraction in all the cases in the experiments that we ran. And channel we did not model explicitly, but that's something we could do also. Good. All right. Thanks.